Okay, let's go through these exercises. As usual, I'm going to do the evens. For homework, you're going to have to do the odds. A lot of the ones that I'm going to do are identical to the ones that you have to do. So I'll try to point out where there's connections. But let's just get started with number 2. And I'm going to give you a heads up that exercise 2 is going to be just like 1. 3 is pretty similar, you just have to do a little bit of algebra in advance. So let's read through this problem. A car rounds a curve with a radius of 25 meters. So we're going to want to set that, the radius of 25 meters. And we have the speed of this car is 20 meters per second. So what we're asked to find is the centripetal acceleration of this car. So before we get into the math, let's talk about what this means conceptually. So think about, we have, let's say this is the center. We have a car. This is our radius. This car is going around a curve. And this isn't quite a circle, but just imagine that wherever this car is at, it's always located 25 meters away, and its speed is always 20 meters per second. So I guess I shouldn't have put velocity here. I should put the absolute value, which basically just means the absolute value of velocity means it's the speed. So when we were talking about acceleration way back in the second 6 weeks of school, we were thinking about it as being a change in velocity, and often that was also a change in the speed. Now when it comes to centripetal acceleration, there is no change in speed, but since this object is always changing direction because it's curving around a circle, that means it's being accelerated. So the acceleration isn't quite the same. You may remember back that and now we're going to call that tangential acceleration, was equal to the change in velocity divided by how much time it took for that change to occur. So that was when we were having a change in speed, but our speed remains constant. Now we have a change in direction. So the formula that we have for the centripetal acceleration is the speed squared divided by the radius, or the distance from around which it's curving, or the distance from the center of its curvature. So this exponent right here gives you a little hint about I guess how many dimensions of space you're working in. Whenever you see an exponent and you're talking about motion, usually has to do with well, not all the time, but in this case it has to do with moving in 2 dimensions. So when you are drawing a circle, or you're expressing the area of a circle, you need 2 dimensions to talk about it. So we have, left and right and up and down here, and that's why this exponent is here. So enough of the theoretics, let's get right into the calculations. The centripetal acceleration is going to be equal to our, not velocity, but speed squared. So that's 20 meters per second. This whole thing needs to be brought to the second power, divided by the radius, which is 25 meters. So let's take care of our numerator. 20 times 20 is 400 meters squared divided by seconds squared. So we divide that by 25 meters. Let's look at what happens to our units. This is going to cancel this out. We have 400 divided by 25. Let's see, 25 goes into 100 4 times. That happens 4 times. 4 times 4 is 16. We have meters up top and seconds squared on bottom. So we still have the same units for acceleration even though we're dealing with centripetal acceleration instead of tangential acceleration. Think of tangential acceleration meaning the change in velocity along the one dimension of motion. So if I had a car and its velocity was going this way, if it was accelerating in this direction or this direction, that would be tangential velocity because it's kind of like in a straight line along this one plane of motion. But when you're dealing with two dimensions of motion, you have to factor in the centripetal acceleration. In centripetal acceleration, just think about the rate at which an object's direction is changing. Not so much its speed, but how quickly it's curving around something. And you can kind of see what happens here. If the radius is larger, it's going to be curving around its center a lot slower. And if this is smaller, it'll be curving around a lot faster. But it varies directly proportionally to the square of velocity. So when the speed is changing, the centripetal acceleration changes exponentially, which is what we're going to get into in the next problem. So anyways, this is the answer. These two have the exact same units, even though conceptually they're a little bit different. This one has to do with more of the change in direction. This one has to do with the change in the speed. But you should hopefully remember that velocity takes into account both speed and direction. That's why it's a vector. So when I take the absolute value here, I forget about the direction and I'm just worried about the speed. Alright, so let's start a new layer. Move on to problem number 4. 1 and 3, like I said, are the exact same. It's just in number 3 you're going to have to solve for a different variable instead of just the centripetal acceleration. So number 4 says, how much larger is the required centripetal acceleration for a car rounding a curve at 60 miles per hour than for one rounding the same curve at 30 miles per hour? So we don't really need to write this stuff down, but I guess let's just write these two velocities down just so that later on we can refer to them. And we're dealing with speed, so I am going to put the absolute value there, even though I'm not going to expect this notation on your quiz. It's just hopefully helping some of you understand conceptually what we're talking about here. So this is miles per hour, and this is 60 miles per hour. All right, so let's just look at our equation here. The centripetal acceleration is equal to the square of the velocity divided by the radius. Now right now we're only concerned about this relationship. So we're going to change this equal sign. This implies, that's what this double arrow or double equal sign arrow that I've been using, it implies that the centripetal acceleration is directly proportional to the square of the velocity. So what happened here to our velocity? It doubled. So then what's going to happen to our acceleration? It's not going to double. It would double if it was only directly proportional to just the speed. But since it's directly proportional to the square of the speed, I won't have to double my centripetal acceleration. I'm going to have to double it to the second power. So this question really calls for kind of a complete sentence. So I'll write it out for you, and you are going to have to do this for number, looks like 11, but I'm going to do number 10, so it'll be just like it for you. So if our speed is doubled, then our centripetal acceleration is quadrupled. So if this was tripled, it would be times 9. If it was quadrupled, this would be times 16. So what we're supposed to see is that if we put a number in here that's twice as large, what we're going to get out here is something that's 4 times, because 2 to the 2nd power is 4. All right, moving on to the next layer, or next problem. Number 5 is going to be similar to letter B on number 6. But first, let's worry about letter A. So number 6 says a car with a mass of 1,200 kilograms is moving around a curve with a radius of 40 meters. At a constant speed of 20 meters per second. And then it tells us about how much it is in miles per hour, but don't really need to worry about that. Okay, so first thing that we need to do in A is find the centripetal acceleration, which we know how to do. We take the speed, square it, multiply or divide that into the radius. This square right here, even if this was negative, like let's say if it was going the opposite direction of our, I guess, where we were looking, our perspective, you could say, it was going away from us or towards us, that negative sign would get taken care of by this exponent. So it doesn't really factor in to the quantity, which actually gives you an idea about how much its speed is changing. It doesn't tell you where it's changing from or to, just how much it's changing. All right, so let's plug our numbers in here. The centripetal acceleration is equal to the square of 20 meters per second. It's important to put this whole thing in parentheses and then square it on the outside, otherwise it looks like the units are squared and you've already done your arithmetic. And we're going to divide this by 40 meters. Okay, so this implies 20 times 20, 400 meters squared divided by seconds squared, all divided by 40 meters. So 400 divided by 40 is 10 meters, cancels out with the square meters. Think about it like this. A square meter is a meter times a meter. You get a meter on the bottom, they cancel out, just leaves you with the meter over second squared. So 10 meters per second in every 1 second. Okay, so that is A. The centripetal acceleration is equal to 10 meters per second squared. Now B asks us to find out what the magnitude of the force required to produce this centripetal acceleration. All right, so hopefully we all remember from the force unit this key equation here. We're only going to change it by one little bit. We're going to call this the centripetal force and the centripetal acceleration. So we have the mass. We just calculated the centripetal acceleration. When we put those two in this equation, and we will be able to quantify the amount of force pulling this thing in its curved direction. That's what the centripetal force is. It's the force that makes something curve around a center of orbit. So 1,200 kilograms multiplied by 10 meters per second squared. 1,200 times 10 gives us 12,000. A kilogram times a meter divided by a second squared. So 12,000 kilograms moving 1 meter in 1 second, or changing 1 meter per second in 1 second. Now let's rewrite this a couple different ways. First, since we're dealing with force, we can write 12,000 newtons. And since we see there's 3 here, what we could do is write, actually, before I jump to that, let's write this in scientific notation first. 1, 2, 3, 4. So 1.2 times 10 to the 4th newtons. And finally, we could also write it as 12, 1, 2, 3 kilonewtons. Whoops. Okay, so all of these are the same exact answer. This is the one that you probably stick with as the easiest, but hopefully you understand why we could change it into this and why this and this are identical. Okay, next problem. Like I said, number 5 is just like number B, or letter B. They just give you this right here. And I think number 7 is pretty much this exact same problem here. All right, number 8. A Ferris wheel at a carnival has a radius of 12 meters. And turns so that the speed of the riders is 8 meters per second. So what is the magnitude of the centripetal acceleration of the riders? Well, we should know. We have all we need already. So let's use the equation that we were introduced to a little earlier. 8 meters per second, all squared, divided by 12 meters. So 8 times 8 is 64, meters times meters, square meters, divided by seconds times seconds, square seconds, divided by 12 meters. All right, so let's see, 12 goes into 65 times. And then we have 4 left over. 4 twelfths reduces to 1/3, which is a repeating 3. My meters cancels out with my square meters to give me meters over square seconds. So 5-point repeating 3 is our centripetal acceleration. This is A right here. All right, B says, what is the magnitude of the net force required to produce this centripetal acceleration for a rider with a mass of 70 kilograms? So this is just like the last problem we did. So we know Newton's second law, slightly modified. The centripetal force, the force that makes objects rotate or revolve around a common center, is the product of the mass of the objects and the centripetal acceleration. So let's plug our numbers in. 70 kilograms multiplied by our centripetal acceleration we calculated from A. So 70 times 5 is 350. 70 times 0.3, what's 1/3 of 70? I'm not sure. So I calculated this to be about 373 point repeating 3 kilograms times meters divided by seconds squared. We'll just call that a Newton. So that's just like number 7. Number 9 is actually pretty tough. Well, no, it's not. It's actually really easy. It's just worded in a way that makes it tough. Let me just read this one to you and make sure that you understand. So for those of you who don't actually listen to these videos, you may struggle with this unnecessarily. It says, what is the ratio of the Earth's orbital period about the Sun to the Earth's period of rotation about its own axis? So as long as you know what an orbital, how long it takes for an orbital period to take when comparing how long it takes for the Earth to rotate around itself, it should be straightforward, and you have the answers in front of you. So make sure you understand why that answer is what it is. Number 10. Joe has a weight of 720 newtons. Which is around 162 pounds when he's standing on the surface of the Earth. What would his weight, the gravitational force due to the Earth? That's probably something that's worth writing down. The weight of any person is really just equal to how strongly the Earth is pulling on them. So these two are equivalent. And hopefully you remember when I showed you this equation, how it's pretty much equal to this equation. Except for G now stands for the gravitational acceleration of Earth. Whereas up here, it could just be any acceleration due to this force. Now we're talking about the gravitational acceleration of Earth due to the weight. Or weight is actually due to the gravitational acceleration of Earth. Alright, so these two are pretty much equivalent, except for now we're talking about the force of gravity, or weight. So, what would his weight be if he doubled his distance from the Earth by flying in a spacecraft? Alright, so there is a new formula to throw at you, but it looks very similar to an old formula. The force of gravity is equal to Newton's gravitational constant, we'll get into that in a second, multiplied by the product of the two masses that are exerting forces on each other. Because remember, forces always come in pairs, so we're talking about two different masses. You can't have a force with just one. Divided by the distance between those masses squared. This should remind you of the electrostatics unit. It's kind of interesting about nature. A lot of different forces are governed by the same type of equations. Both of these formulas right here are known as inverse square laws. So there's a couple other ones. The other one I'm thinking of is brightness, like how quickly something's brightness drops off when you are increasing the distance from it. Inverse, because the thing that is squared is in the denominator here. So the one that we're focusing on, the force of gravity. What's kind of interesting about this is you can see what G is equal to if you look at this equation. If we just focus on this one mass right here, we can see that the Earth's gravitational acceleration is actually equal to all of these things right here in this little circle. So let me try to put all that together. Newton's gravitational constant multiplied by the other mass it's interacting with via gravitational field, just like this is the electrostatic field, divided by the distance between them squared. So this right here, this whole thing, that's G. The Earth's gravitational acceleration, or really any, so this right here is the mass of the Earth. This would be the mass of the object being attracted to Earth, which is what causes it to have weight. That's equal to Newton's gravitational constant multiplied by the mass of whatever is doing the attracting divided by the distance from that object squared. Alright, so I just went off on a huge tangent here, but it's more just to introduce this equation right here. All you really need to know for this problem is that the force of gravity, which I want you to know is also equal to weight, is inversely proportional to the square of the distance. So let's go back to this problem. So if Joe doubles his distance, okay, what's going to happen if this distance doubles? So the force of gravity, or the weight, is not going to go up, or sorry, it's not going to go down by a factor of 4. Remember, these are inversely proportional. So the force of gravity, or weight, is inversely proportional. This drops off much quicker and actually blows up way quicker due to this exponent. So it's not just going to double, or I'm sorry, it's not going to go down by a half. It's going to have to go down by 1/2, or 1/2 squared. So it's going to change based off of, if this r is being doubled, then it's going to go down by a factor of 4. Okay, so really what we need to do is take this weight of 720 newtons and multiply it by a factor of 1/4. So we're really just saying 720 divided by 4. So that means, I'm sorry, I got one more there. So that means his weight is going to be equal to 180 newtons. So if the distance gets doubled, that means that the weight is going to be dropped by 1/4 because of the inverse square law. All right, so number, let's see, 11 is just like this. You just are given a different distance. I believe it's tripled or something like that, which should tell you that this isn't going to be a 4, it'll be 3 to the 2nd power, and anything more, and I'll be giving you the answer. All right, number 12, getting close to the end here. Number 12 states that there are two 200 kilogram masses. So mass 1, 200 kilograms, and mass 2, 200 kilograms. Two 200 kilogram masses are separated by a distance of 1 meter. Find the magnitude of the gravitational force exerted by one mass on the other. Doesn't matter which, since forces always come in equal and opposite pairs. So we're going to use the formula that represents universal gravitation. But we need to address this constant now. So you should be able to figure out what the units should be. Let's start with that. The units for this, they have to have a newton in it, that's for sure. And we want everything else to cancel out. So what's on the bottom here? We have meters squared. So up top we're going to want meters squared, so that when we multiply this by this, our meters squared are going to cancel out, leave us with a newton. But what needs to be on bottom? Well, what do we have up here? A kilogram times a kilogram, or kilograms squared. Oops. So those are our units. Now for the experimentally derived, or experimentally determined number. Very small number. And looking at this, you can automatically tell what you're going to have to be able to do on your next quiz. That's right, use scientific notation. I taught you how to do it with the calculator, and I taught you how to do it with arithmetic. I'm not going to be able to practice the calculator in front of you here. Maybe I can pull up a website where you can actually see me punch it in, but I feel like that'll be taking too much time, so we'll just practice it using the rules of multiplying when we have a common base. All right, so let's plug our numbers in here. 6.67 times 10 to the negative 11. This negative 11 right here lets you know how small the force of gravity is, especially in comparison to the electrostatic force. Remember that K, it had an exponent that was, I think, positive 10 right here. So it's, I don't know, it'd be 100 times larger. Anyways, that kind of gives you an idea about, oh, messed up, why the whole Earth isn't pulling you towards the center, because the electrons in your body are pushing against the Earth's surface much stronger, like 100 times stronger. So up top we have our two 200 kilogram masses. And then on the bottom here, 1 meter squared. Just makes it too easy on us. All right, so how should we approach this? I think the first thing that we should do is multiply these two together. So let me rewrite this down here. 6.67 times 10 to the negative 11 newtons multiplied by a meter squared over a kilogram squared. And 200 times 200. So we might as well divide this into it right now, and we'll multiply everything together in a second. So 2 times 2 is 4. 200 times 200, all we really have to do is take a 4 and then add, or not add, but attach those 4 zeros at the end there. Kilograms squared over, we could say 1 times 1, but we know that's 1. And anything divided into 1 is just 1. So let me get rid of that line, and we'll just call it what it is, square meter. Normally it's not going to be that easy. Okay, so here's the fun part, dealing with these exponents. Let's say 6.67 times 40,000. And then we'll multiply that whole thing by 10 to the negative 11. All right, so let's get a calculator up here for you. So we have 6.67 times, what was it? 40,000. 1, 2, 3, 40,000. So we have 266,800. Times 10 to the negative 11. Now let's look at what cancels out here. Our kilogram squared cancels out with these kilograms squared. Our meter squared cancels out with these meter squared newtons. Now this technically is the correct answer, but let's say I want to move this back here. 1, 2, 3, 4, 5. So you might think that would make this more negative since I'm going back, but actually since the decimal place is way over here because of this negative sign, I'm getting closer to it. So how much closer did I get to it? 5. So I'm getting less negative by 5. So I have 2.668 times 10 to the negative. I went back 1, 2, 3, 4, 5, so that makes this times 10 to the negative 6 newtons. And that is the correct answer right there. So notice I only had to break out the calculator when I dealt with this and this. Sometimes you'll have exponents over here, like I could have said 4 times 10 to the 1, 2, 3, 4, and added up my exponents later. Hopefully you remember how to do that. If not, don't worry, you're going to get some practice when it comes to the calculations review before your quiz, but stuff is not that bad once you get used to it. Hopefully this is refreshing your memory. Okay, I think we have 2 more problems to go. Let's see, that was 12. 13 is just like number 10 that I did, and 11. So 11 and 13, you're pretty much doing the exact same thing that you did with me on number 10. So number 14. The acceleration of gravity at the surface of the moon is approximately 1/6 of that at the surface of the Earth. So we know the gravitational acceleration at the surface of the Earth is 9.8 meters per second squared, approximately. And the moon's gravitational acceleration, is about 1/6 of that. So we don't actually need to calculate that, but if we wanted to, what we would do is multiply it by 1/6. And actually, let's do that. 9.8. I could say times 1/6, but 9.8 times 1 divided by 6 is the same thing. Oop. It gives us, well, 1.6 repeating 3. So this is how much less. Like when you're on Earth and you're falling 9.8 meters per second faster for every 1 second that goes by. Whereas on the moon, you're falling 1.6 repeating 3 meters per second faster for every 1 second that you're falling. So the main thing I'm trying to show you here, and it's really just to get you set up for success on the next problem, because you are going to have to set up a proportionality like this, is that when you are, oh, I'm sorry, let me take away most of what I just did. When you divide one by the other, what you get is this fraction, 1/6. The gravity of the moon, or the gravitational acceleration of the moon, divided by the gravitational acceleration of Earth is 1/6. If I divided this by this, I would get this ratio. So, going back to the problem. What is the weight of an astronaut standing on the moon whose weight on Earth is 180 pounds? So this problem is pretty easy. Let me show you the hard way how to do it first. What we want to do is say, all right, we know the ratio of these two. Even if we didn't know the ratio, if we were just given these values, we could find that ratio. What I want to know is, what is the weight of this person on the moon? And I could also use this over here. Same thing. If we know the weight of this person on the Earth. Well, you all know how to do cross multiplication. If I'm solving for this right here, then I would multiply these two right here and divide by this right here. So I don't want to do that. What I'm going to do is go through the algebra, multiply by the weight of this person on Earth on both sides. That cancels that out. So the weight of this person on the moon is going to be equal to their weight on the Earth multiplied by the ratio of their weight, the gravitational acceleration of the moon on the surface divided by the gravitational acceleration of the Earth on its surface. So now we can plug in these numbers. And I never wrote down what their weight is on Earth. So let me write that down over here. Their weight on the Earth is 110 pounds. So their weight on the moon is going to be 110 pounds multiplied by this ratio right here. So I could divide this by this, but we already know what it is, 1/6. So what's 1/6 of 110? 18 point repeating 3. Or we could say 18 1/3. So just whatever your weight is right now, divide that number by 6. That's how heavy you would feel if you were on the Earth. Or I'm sorry, if you were on the moon. About 6 times lighter. So another thing about this proportionality, if I was to change up these ratios right here, you would you'd get the mass of the people. Remember, weight equals mass times gravity. I divide gravity on both sides, and I get the mass of anything is going to be the quotient of its weight and the gravity. So if I was to multiply this over here, then bring this over here, and this over here, basically made it so that these were both equal to each other. The quotient of their weight and the gravitational acceleration is always going to be the same. Remember, your mass will not change regardless of where you're at in the universe. However, your weight will change because the gravitational acceleration of whatever planet you're on is going to change. Because when it comes to what g is actually equal to, this right here is going to change. And if you get further from that object, this right here will change too. All right, last problem. And real quick, just before you try to do number 15, you're going to have to set up a proportionality like this. But you're not going to be dealing with the moon. I think you're going to be dealing with Jupiter. And you may not have the Earth in the bottom. You could flip these two around and it would be the same proportionality. But anyways, hopefully you figure it out. Last problem, number 16. This one doesn't actually involve too much math. It's more just reasoning. But that's a good process to practice before your quiz. So if the time separating high tides is 12 hours and 25 minutes. So let's call that the period between tides. And it says high tides, but it's going to be the same for low. Is equal to 12 hours and 25 minutes. I could turn this into I don't know, the fraction out of like 25 out of 60 and say 12 point whatever hours, but I think that's going to make it unnecessarily complicated. So if the high tide occurs at 2:10 p.m. one afternoon, let's write that down right there. So this T right here, this represents period, which is the time between cycles. The high tide happens at 2:10 p.m. one afternoon. At what time will high tide occur the next afternoon? So, tides happen twice a day. So the next afternoon, 12 hours from 2 p.m., well, that's going to be 2 a.m. And 25 minutes after 2:10 a.m. will be 2:35 a.m. That's not the afternoon. What we're talking about is when that cycle of tides gets all the way back 24 hours later pretty much. And it's not exactly 24 hours later, it's 24 hours and 50 minutes later. And that's because the moon is revolving as the Earth is rotating. So I'm probably going to do a terrible job trying to show you this, but just think about when the Earth revolves around itself. The moon is also going to be, when the Earth rotates around itself, the moon is going to be revolving, but it only makes its way about this much, let's say. So by the time the Earth gets back to here, 24 hours later, it's not quite high tide yet. It's got to get all the way back to here to account for the moon's orbit. So that's where this extra 25 minutes comes into play, or actually 50 minutes comes into play. All right, so if it's 2:10 p.m., and just so you know, this is A, we're looking at not just 12 hours later, 12 hours times 2, 24 hours later. And not just 25 minutes later, 25 times 2, 50 minutes later. So 24 plus 2:10 p.m., that's going to be 2:10 p.m. But we still have to add together this 50 minutes. So for A, the next time that there's going to be high tide, or the next afternoon, will be it will be 3 p.m. All right, B. When would you expect low tides to occur the next day? All right, so the low tides are going to be halfway between the two high tides. Remember, these tides are due to the Earth's rotation around itself. So it's about every 6 hours, or 6 hours and 12.5 minutes, because that's half of this time. So let's just say the time between the highs and the lows is about 6 hours and 25 minutes. Or I'm sorry, 6 hours and 12.5 minutes. Half of this, half of this. So high tide would be 12 hours, 12 hours. Low tide would be 6 hours and 12.5 minutes, and then another 12 hours and 25 minutes. So when would you expect the two low tides to occur the next day? Well, the next day, let's see, if it's 2:10, 6 hours is going to bring us into the next day. So 6 hours later after that, it's not going to be low tide, it's going to be high tide again. Then we need 6 and 12.5 minutes after that. So let's bring us to our next high tide, which would be, so let's base it off of this point. The next high tide is going to be 12 hours after 2:10 p.m. is going to be 2 a.m. and 25 minutes after 2:10 would be 2:35 a.m. So now we need to know, when is it going to be a low tide? Well, it's going to be 6 hours after that, halfway to the next high tide. So we could have subtracted from here if we wanted to, but let's add from here. I think it's easier to add time than to subtract it. So the first tide of the day is going to be a high tide at 2:35 a.m. And halfway into the next high tide right here is going to be where there's a low tide. So we have to add 6 hours. And then half of 25 would be 12 minutes plus 30 seconds. So 6 plus 2 is 8. 35 plus 12 would be, let's see, 45, 47, and 30. So the first low tide is going to be 8 hours, 47 minutes, and 30 seconds. So that's low tide number 1. Now if we wanted to, we could add 12 hours and 25 minutes, or we could go to this 3 p.m. right here and repeat this process, which I think will be easier. So let's do that. 3 p.m. plus 6 hours plus 12 minutes plus 30 seconds. So 3 hours plus 6 hours is going to be 9 o'clock plus 12 minutes. It would be 9:12 and 30 seconds. And that's p.m. So here's low tide number 2. Alright, so that takes care of our last exercise. You are going to need to do 1, 3, 5, 7, 9, 11, 13, and 15. And this will be the last set of exercises you do this year.